Danny is the last speaker this morning. He's the archetype of, again, scientific versatility. Danny is a professor at Princeton University. His work spans experimental, field, and modeling studies. He's made numerous important contributions, including the development of an analytical protocol for nitrogen isotope biogeochemistry. That's a cornerstone for nitrogen isotope biogeochemistry. Danny is fluent in current and oceanic biogeochemistry, both in terms of carbon and nitrogen currency. And today, Danny will talk about nitrogen isotope-assisted view of Southern Ocean nutrient cycling.
Sign will stay up for about 30 seconds, so just keep
going. Okay, and the forward slide is the...
Yeah, try it and see if it works. Yep.
Yes, indeed. Okay, my charge today is to take you through some of the basics of Southern Ocean biogeochemistry. And I'm going to be doing this largely using the nutrient distributions of the ocean. And later in the talk, I'm also going to turn to the isotopic composition of nitrate, the most common form of nitrogen supplied to the surface ocean, as an additional probe for Southern Ocean nutrient cycling. And one of the goals there is to show you some of the complementary information we get from the isotopic composition of nitrate, so the isotopic composition of a nutrient species relative to just its concentration. But that will be at the end of the talk, so we'll see how this goes. These are the contributors of the isotopic data, if I get to it. So I want to start out with, it could be called the Ito slide if you wanted, which frames the Southern Ocean in the context of the global biological pump. And so what we have here, I can't see anything, so I'm going to come around here, let's talk about the ocean without the Southern Ocean, if we may. And so what we've got here is a surface ocean and an ocean interior. We've got three colors of arrows here. The blue is for water. The black is for phosphate, which will be our canonical nutrient. I'm going to switch over to nitrate later in the talk because my slides do. You can think of them as being the same in the context of what I'm going to be telling you about. And then the last color is orange, and this is for carbon, for CO2. And so we've got nutrients in the ocean. We've got phosphate. And it is brought into the surface ocean by a variety of processes. And in low latitude ocean, almost all of this nutrient is consumed by phytoplankton. And this leads to a rain of organic matter into the interior. This will transfer the phosphorus back into the ocean. It'll be broken back down by bacteria to phosphorus within the ocean interior. And then we're going to call it regenerated phosphate. Okay? This organic matter, of course, is also going to be carrying carbon into the ocean interior. And so you will be taking CO2 out of the surface ocean and the atmosphere with which it's equilibrating, and will store that carbon as excess CO2 in the interior. So this transformation of the phosphate pool into regenerated phosphate will store carbon in the ocean interior, thus the global ocean's biological pump, where by biological means sequestering CO2 in the ocean interior. And the strength of this process today, something like 250 ppm effect. The water, we're going to need to get the water back down somewhere. And to a large degree, the way that this nutrient-stripped water returns into the ocean is through North Atlantic deepwater formation in the high latitude North Atlantic. So if this was all we had, in fact, we'd have an even more efficient global, biological pump than we have today, and carbon dioxide concentrations would be lower. But we don't. We also have the high latitudes, and specifically we have the high latitude Southern Ocean. And so in the Southern Ocean, we've got nutrients, we've got water coming to the surface very quickly. This is carrying nutrients to the surface very quickly. It's sort of an aspect of oceans geochemistry that if you're bringing nutrient-rich water to the surface very quickly, it will end up leading to conditions which are whereby phytoplankton are only able to consume a very small fraction of the nutrient supply. So in this end-member case, as I've shown it, basically there is no biological extraction of this phosphate, and all the phosphate will return with the water into the interior as preformed phosphate. This water came up charged with both phosphate and CO2, but it's going down equilibrated with the atmosphere. So CO2 has escaped back to the atmosphere in this picture. So what we have here in this southern loop is basically this process of transforming phosphate back into preformed phosphate is this preformed phosphate, you can think of it as a missed opportunity for carbon storage in the ocean interior. So when you think about ways by which the Southern Ocean, let's imagine I'm thinking about ice ages, and I pretty much always am. How we might lower atmospheric CO2 by strengthening the global ocean's biological pump, I have two options with regard to this cartoon. One is I could just make this side go away. Okay? I could cut off the Southern Ocean loop such that all the nutrients in the ocean would be regenerated, and I'd have maximal storage of CO2. The other option is to make the nutrient conditions in the Southern Ocean surface look as much as possible like the low latitude loop. That is to say, to increase the degree to which nutrients are consumed in Southern Ocean surface waters. Essentially, that's also canceling the side by just making it look like that side. Okay. So this is a pretty simple framework for understanding why the heck one would study the Southern Ocean over glacial and interglacial timescales with regard to carbon dioxide. But today, I'm really focusing on the modern Southern Ocean. And so I want to make this cartoon a little bit more real by referring to ocean data, nutrient data. And so what's shown here are two depth sections through the ocean. These are from Sarmiento and Gruber. And they're amazing things. So this is the Nicky Gruber font. And what this is a virtual, very long cruise from on the left side. So we've got depth on this axis, a blow up of the upper 1,000 meters here, 1,000 to 6,000 meters down there. We're going from the high latitude North Atlantic southward to the Southern Ocean here, around the Southern Ocean into the Pacific sector, and then northward into the Pacific sector. Got it? Okay. Now the upper plot is for this parameter I just described, preformed phosphate. This is this missed opportunity phosphate in the ocean interior. And down here we have regenerated phosphate, phosphate stored with regenerated carbon and thus storing excess CO2 in the ocean interior. So let's go ahead and look at the preformed phosphate map. What you can see, as I promised, is that North Atlantic deep water is bringing the low nutrient content of the low latitude surface ocean into the interior. It's bringing in low preformed phosphate. And in contrast, the Southern Ocean here, where there is incomplete consumption of nutrients in the surface, we have we have preformed phosphate entering the ocean at two depths, and these correspond to this upper and lower cell that we've been hearing about. With regard to the lower cell, we have Antarctic bottom water, which is rich in unused nutrients, and it's coming in both into the Atlantic sector and here into the deep Pacific sector. And throughout the Pacific, we basically have a mixture in terms of ventilation of North Atlantic deep water and Antarctic bottom water. And so we have an ocean interior that has a lot of preformed phosphate in it due to the high preformed nutrient nature of Antarctic bottom water. We also have Antarctic intermediate water and subantarctic mode water, the subducted products of the upper cell that we heard about earlier. And because surface nutrients are not completely consumed across essentially all of the Antarctic zone, the more southern part of the Southern Ocean, these are coming into the ocean interior. Okay, so if Antarctic bottom water were not bringing in high preformed nutrients into the interior, then the regenerated nutrient concentrations, and thus the CO2 storage in the deep ocean, would be greater, and this storage would be down here. If Antarctic intermediate water and subantarctic mode water, there's one thing I wanted to mention about this upper loop. So this high preformed nutrients, these high preformed nutrients that are coming into the low latitudes from Antarctic intermediate water and subantarctic mode water, they have an additional benefit, and you can see them here in the regenerated phosphorus plot. They bring in nutrients to the low latitudes. The low latitudes that generates productivity in the surface ocean of the low latitudes. That leads to sinking organic matter. That then it's regenerated to regenerated nutrients, and so you have a pileup of regenerated and preformed nutrients in the low latitudes, and that is important for low latitude biological production. Okay, so I already told you what happens if I were to lower the preformed nutrient concentration of Antarctic bottom water. If I were to lower the preformed nutrient concentration of Antarctic intermediate water and subantarctic mode water, this is not a whole heck of a lot of water. So its conversion to regenerated carbon doesn't in itself store a lot more carbon dioxide in the ocean interior. But there's a couple of interesting effects. One is that by shutting off these preformed nutrients into the mid-depth oceans, you'd also be shuffling these regenerated nutrients, you'd be shuffling these regenerated nutrients as well into the deep ocean. And so in net, if you reduce the preformed nutrient content of this mid-depth water, you end up lowering low-latitude biological production. One possible outcome for this from the perspective of calcium carbonate on a 1,000-year time scale is that with lower calcium carbonate production across the global ocean's alkalinity needs to rise. And you'll also be increasing the regenerated nutrient burden and thus the excess CO2 storage down here in the deep ocean. And that will preferentially lower the saturation state for the preservation of calcium carbonate in the deepest ocean. And that will also drive the ocean's alkalinity to rise. And ocean alkalinity rise beyond the biological pump picture that I showed you before is another mechanism for storing CO2 during ice ages. And so all this to say is that this upper loop, this upper cell, while it doesn't ventilate much of the ocean interior and thus doesn't have much oomph in terms of global ocean preformed nutrients, bats above its level for CO2 lowering because of these effects on calcium carbonate dynamics. So now what I'm going to do is zoom in on the Southern Ocean and look at its hydrography in some detail. And so this is a section starting from the south going northward here. So here we have the Antarctic continent over here. So the Southern Ocean is separated into these fronts. The Antarctic zone south of the polar front, and you can separate that as well if you'd like. Then we have the polar front northward to the subantarctic front. It's where the polar frontal zone is found. And then from the subantarctic front to the subtropical front is where the subantarctic zone is found. And so in terms of the two cells that we talked about before, the lower cell in a hydrographic sense is largely described by lower circumpolar deep water that's being brought up to the surface, forming Antarctic bottom water, but also exchanging with Antarctic bottom water. And there are a lot of processes, obviously, in this region that we just simply don't understand. And then here in the upper cell, we've got upper circumpolar deep water, which is feeding the residual circulation. With then subduction of this water is Antarctic intermediate water here and subantarctic mode water here in the upper 1,000 meters. And these waters are going to be eventually subducted back into the deep ocean. Lynn was referring to this later in North Atlantic deep water formation. And so when I said before that the upper cell doesn't really get to ventilate much of the interior, this is the issue. You're only forming these mid-depth waters, and then it's going to be the North Atlantic, the nutrient consumption in the low latitudes, and sinking in North Atlantic that resets their chemistry. Whereas the lower cell gets to ventilate the abyssal ocean freely, only being limited by how much it's competing with North Atlantic deep water formation. Okay, so let's look at these different water masses in terms of their biogeochemical characteristics. Well, first in the top we have temperature and salinity. So what I'm showing you here are sections from the Pacific sector. Again, we've got depth on the y-axis, and we're going away from the Antarctic continent. The latitudes are shown up here. This is temperature. Salinity is over here. Now the biogeochemical parameters, dissolved oxygen down here, and nitrate over here. So what characteristics can we identify in the interior? Well, lower circumpolar deep water here shows up as a maximum in salinity, this yellower color in salinity. This is due to lower circumpolar deep water deriving from having a contribution from North Atlantic deep water, which raises its salinity. Subantarctic mode water, Antarctic intermediate water in particular, are deriving from the Antarctic surface, or the Antarctic intermediate water is right at the polar front, and subantarctic mode water are only somewhat a little bit northward at the subantarctic front. And here salinities are low, and so we're injecting low salinity water into the interior. interestingly, upper circumpolar deep water, which is going to be part of this upper limb, it's not really characteristic in terms of its salinity. It's intermediate between lower circumpolar deep water and Antarctic intermediate water here. We can see Antarctic bottom water, a tiny bit of Antarctic bottom water showing up just to the south side of these sections. This is just sampling some larger mass that's probably over there. It has a slightly lower salinity but a colder temperature than lower circumpolar deep water, than North Atlantic deep water, which makes it somewhat denser than North Atlantic deep water, and in turn denser than lower circumpolar deep water. So it would flow below lower circumpolar deep water, all else held constant for this depth level. Now, we said that upper circumpolar deep water didn't really show up in salinity, and that's because upper circumpolar deep water doesn't derive from any region of the surface ocean. It is produced in the interior. And upper circumpolar deep water is very characteristic in its nutrient chemistry. So here we see in nitrate concentration, the highest nutrients in the profile at these mid depths is associated with upper circumpolar deep water. Actually, this mass over here is Pacific deep water, which is transformed, which communicates with upper circumpolar deep water, and upper circumpolar deep water feeds this highest nitrate water up to the surface. Antarctic intermediate water and subantarctic mode water have lower nutrient concentrations, and this is due to the fact that while there's not much nutrient consumption in the Antarctic surface, there is some, and this thus lowers the nutrients that are then subducted into the interior as Antarctic intermediate water and subantarctic mode water. Now, when it comes to looking at lower circumpolar deep water and Antarctic bottom water relative to one another, the picture gets kind of fuzzy in terms of how to explain these. If you jump across here to oxygen for a second, one of the things we expect is where we're going to find the highest regenerated nutrients, where that's in fact the definition. But this high regeneration, or a big burden of regenerated nutrients and carbon, will also come with an oxygen deficit. And here we see that appropriately upper circumpolar deep water has low oxygen, and this is oxygen minimum all the way up to the surface. And this is often actually how upper circumpolar deep water is defined hydrographically, as this depth-wise oxygen minimum. Antarctic bottom water shows up here as having high oxygen, both because it's cold and it's newly formed here. But to understand better the relationship of Antarctic bottom water, lower circumpolar deep water, and upper circumpolar deep water, let's go again to preformed nutrients. And here we're looking at preformed and let's look at preformed and regenerated nutrients, and here we're looking at preformed and regenerated nitrate. So in the upper plot here, we've got preformed nitrate for these same sections, so we're going from south to north, depth on this axis. The preformed, the orange colors are higher, so unused nutrients at the surface propagating into the interior are going to be more orange or red here. So what do we see? Well, for preformed nitrate, lower circumpolar deep water is a minimum. That makes sense. We said before that North Atlantic deep water is this low preformed nutrient end member in the global ocean, and it is contributing in particular to lower circumpolar deep water when it flows into the Southern Ocean. Lower circumpolar deep water and upper circumpolar deep water are upwelling to the surface, and there, as we've described, nutrient consumption is highly incomplete. And so in this case, you're transforming regenerated nutrients into preformed nutrients, that is to say unused nutrients at the surface. And they're then sinking into the interior. Here is Antarctic bottom water. The bottom water is probably forming somewhere over here and coming into the picture from over there, but fine. And here we have Antarctic intermediate water subducting as this very clear high preformed nutrient tongue reaching to low latitudes. So where in the world, where is upper circumpolar deep water or Pacific deep water in this picture? We can get a handle on this by looking at the regenerated nitrate section as well. So here we have Antarctic bottom water and lower circumpolar deep water, son of North Atlantic deep water. Antarctic bottom water wants to fill the flow into the Pacific and fill it, and it's on the way, it's mixing with lower circumpolar deep water, and so they move in together into the deep Pacific. Within the deep Pacific, they end up upwelling to mid-depths, and this is at least partially driven by, over a very long time scale, mixing with the low salinity waters of Antarctic intermediate water, raising their buoyancy and thus allowing new deep waters to form in below them. But in any case, Antarctic bottom water and lower circumpolar deep water rise up toward the surface to Pacific deep water. This is where, over this long time that this is happening, organic matter is continuing to rain into the ocean interior. That's being broken down by bacteria to regenerated nutrients. And so we see this regenerated nutrient maximum associated with Pacific deep water and upper circumpolar deep water. And here, upper circumpolar deep water is upwelling toward the surface. And it's going to come up here, and regenerated nutrients are going to be converted to preformed nutrients, subducted here, and CO2 is escaping to the atmosphere in this sense. Okay, so what I'd like to do now is show you a complementary picture of this Southern Ocean hydrography and in its interaction with biogeochemical processes that we can get from looking at the isotopic composition of nitrate. How much time do we have here? Thanks. Okay, so two stable isotopes of nitrogen, N14 and N15. For oxygen, we're just going to be focusing on two of them. So we're going to be looking at the N15 to N14 ratio of nitrate and the O18 to O16 ratio of nitrate. We describe these in terms of their delta N15. This would be a higher delta N15 has a higher N15 N14 ratio. A higher delta O18 has a higher O18 to O16 ratio. And sorry, this is nitrate down here, NO3 minus, you've seen before. And the key process that gives us information here is that when phytoplankton in the Southern Ocean surface consume nitrate, they preferentially consume N14 nitrate and O18 and O16 nitrate. That's what all this stuff says. And so you end up producing low delta N15, low N15 or N14 organic matter, and you leave behind nitrate that's high in delta N15 and high in delta O18, high in N15, N14, and high in O18, O16. This is and so let me take you through these schematics quickly, which compare how to think about the effects of different biogeochemical processes on nitrate delta N15 and on nitrate delta O18. So we've got a plot of nitrate delta N15 versus nitrate concentration and delta O18 versus nitrate concentration over here. When we have nitrate assimilation occurring, of course, we're going to lower nitrate concentrations because we're producing organic matter from that nitrate. And associated with because you're preferentially consuming N14 nitrate, the delta N15 and the residual nitrate rises. It turns out that this is also true for the delta 18 of nitrate, okay? And it has the same amplitude. The isotopic effect has the same amplitude. For regeneration, the organic matter that you put back into the water when you break down that organic matter to nitrate, that'll take you to the right on this axis to higher nitrate concentration. And the delta N15 can be really whatever is being remineralized. So if you produced low delta N15 organic matter and it's now being remineralized into water, it'll lower its delta N15. If, let's say we have deep nitrate in the deep Pacific and there's high delta N15 organic matter raining into it for some reason, it'll raise its delta N15. The delta 18 is altogether simpler. The delta 18, the new nitrate you produce has no memory of the nitrate of anything except the nitrification process. So regardless of what the nitrate delta 18 was that was previously consumed, the nitrate delta 18 you're going to be producing by regeneration is constant. And this is a useful thing when using the two isotope systems. So here's what we see for nitrate delta N15 and delta 18 for a section in the Southern Ocean here. So a set of depth profiles. So nitrate concentration on the top, delta N15 here, delta 18 here. So let's familiarize ourselves with this top diagram. We've got the south again over on the left here, going northward there, down to 2,000 meters. So here as before, there's this nitrate maximum associated with upper circumpolar deep water. Lower circumpolar deep water is characterized by this lower nitrate concentration. And then on the south side of this section, there's this big mass that we are only partially sampling here known as Weddell-Sea deep water, which is basically lower circumpolar deep water. I think of it this way, as lower circumpolar deep water and a component of Antarctic bottom water that are relatively stagnant in this region, just sort of accumulating a nitrate from regeneration. Now, what do we see in the nitrate delta in 15? If we compare, just look at the gradient in nitrate delta in 15, starting from upper circumpolar deep water upward relative to the nitrate concentration, everything makes perfect sense. So we're bringing up high nitrate water, only consuming a fraction of it, but we are consuming a fraction of it, and then subducting a lower nitrate concentration water in the form of Antarctic intermediate water and subantarctic mode water. So we're bringing up nitrate here, partially consuming it. That leaves the residual nitrate higher in delta in 15. That then gets transported northward and subducted as Antarctic intermediate water and subantarctic mode water. Similarly, for nitrate delta 18, we bring up something with a lower delta 18 and subduct something with a higher delta 18. Okay. Where things get a little bit more interesting is as we compare these other waters further to the south with one another. So here nitrate concentrations are lower, here they're higher, and yet so as we go from Weddell Sea deep water to LCDW to upper circumpolar deep water, we're going from higher nitrate concentration to lower nitrate concentration to higher nitrate concentration again. In delta in 15, it's monotonic. We're going from lower delta in 15 all the way through to higher delta in 15. What's going on with Weddell Sea deep water is that we're in a region where we've consumed low delta in 15 nitrate. We've converted that to organic matter, and that is sinking into the interior. And so that is being remineralized as low delta in 15 nitrogen nitrate and producing this low delta in 15 nitrate burden here in the deep Weddell. What I want to do now is show you what this looks like on a very large scale, and this is where I'll stop. So we're back to the Pacific sector here. We're in the central Pacific. We're looking at a transect from south to north. This is P16S again. So near Antarctica, northward here. And we have a blow up of the upper 1,000 meters here and then down to 5,000 meters here. And the panels are nitrate concentration, delta in 15, and delta 18. So here we can see in the upper water the subduction, the nutrient effects of the subduction of Antarctic intermediate water and subantarctic mode water, producing lower nutrient thermocline waters, SAMW and AIW. And associated with that, the delta, we're subducting higher delta in 15 nitrate into the thermocline here. Similarly, we're subducting higher delta 18 nitrate. These have been partially assimilated and so increased in nitrate delta 15 and delta 18 and then put into the interior. If we then go down to the lower picture, the whole 5,000 meters of profile, we can see what the whole structure looks like. So here is this subducted high delta 15 nitrate and high delta 18 nitrate from Antarctic intermediate water and subantarctic mode water. On the other hand, over here toward the south, we have the very low delta in 15 of circumpolar deep water, lower circumpolar deep water, and Antarctic bottom water associated with the fact that to make these waters high in delta in 15 and delta 18, we needed to preferentially consume N14 rich organic matter and sink this stuff into the interior. When it sinks in there, it lowers the delta in 15 in this region. So this low delta in 15 is the complement to this high delta in 15 over here. Okay, so one of the interesting things we can see here now, looking at the full delta in 15 structure, is that the delta in 15 of Pacific deep water here is higher than both lower and so this Pacific deep water then feeds into upper circumpolar deep water here, is higher than Antarctic bottom water and lower circumpolar deep water. And so to return to the picture we've already gone through in the context of nitrate, we're bringing in Antarctic bottom water and lower circumpolar deep water here. They're upwelling into the mid-depth Pacific. As that happens, they're accumulating regenerated nitrate. That's raising the nitrate concentration at mid-depth. And then this high nitrate concentration water is communicating as upper circumpolar deep water to be upwelled in the northern cell of the Southern Ocean circulation. As this process of modification of lower circumpolar deep water and Antarctic bottom water transformed to Pacific deep water, the delta N15 is rising. Okay? Now, why is the delta N15 of this nitrate rising? Well, we're seeing that there's an increased accumulation of regenerated nutrients or nitrate at this depth. You could argue that maybe you're just mixing down high delta N15 nitrate from above down into this water. But we can say that that's not occurring because we have the nitrate delta 18 data. And if it was happening, we're mixing down high delta N15 nitrate, we'd also mix down high delta 18 nitrate. What's happening is this high delta N15 nitrate that we see through the global ocean is shuffling high delta N15, is producing high delta N15 organic matter in the overlying surface waters. That's sinking into the interior. And that is then being remineralized and raising the delta N15 of Pacific deep water. This water then flows back as upper circumpolar deep water into the Southern Ocean circulation. And on its route, one thing we know is that its delta N15 falls as it enters the Antarctic. And again, this is because we have sinking material with a low delta N15 in this region, returning it. And so in this sense, we have an isotopic, we can close the budget for the nitrate isotopes. And we see evidence for these two cells that are suggested by the circulation and suggested by the hydrography. So I'm actually going to stop there and take questions.